All right. Let's go back. Okay, so now we're gonna look at a different scenario. Now, all of these SN2 reactions,
Mm-hmm.
they were occurring between two molecules, two different molecules. So we say this is intermolecular. Inter meaning between two molecules. All right.
Mm-hmm.
Now, what we're going to do, we're going to look at a scenario where the SN2 reaction is occurring within one molecule. And we call that intramolecular. All right, so we can have this scenario here. So we can have this molecule here.
Mm-hmm.
Right? What are the components of an SN2 reaction? What do you need?
A substrate, a leaving group, and a nucleophile.
What does the substrate have?
Has a R group and an alcohol. Or I mean R group and an halogen.
Okay. Now remember that we said that for the most part our substrate for now is going to be an alkyl halide. All right. Doesn't mean it can't be something else. So in the later units you're going to see it with an alcohol. You're also going to see it with an ether. All right. But for now we're in this domain. All right. That's where we're at. Cool.
Mm-hmm.
Notice that this is one molecule. Right?
Mm-hmm.
Now, in this one molecule here, I have my alkyl halide, or let's just say substrate. What is the other component of the SN2 reaction? We have a substrate and
you have your halogen.
that's right, which is part of the substrate.
Okay, and you have your nucleophile.
Perfect. So I have my substrate here, and I have my nucleophile, so I can react. I can go ahead and do the reaction. So my nucleophile will attack the carbon of the substrate containing the leaving group, and the leaving group will leave.
Mm-hmm.
And since this is occurring at the same time, it's SN2. Right?
Yeah.
Now, the best way to do this is to count the carbons. So we can count this, call this guy 1, this guy 2, 3, 4. Right? And we can generate
Mm-hmm.
and this would be 1, 2, 3, 4. On the fourth position, I have this NH2 group. This here is going to have a positive charge, so I will just have to deprotonate, and I can deprotonate with this I minus. Right, so I generate I minus, right, and I can use that I minus to deprotonate one of these hydrogens. To form this. Right? So this here is an intermolecular SN2 reaction. Right?
Yeah.
So we looked at the intermolecular, intra, intra, not inter. Is an intra molecular SN2 reaction.
Are all SN2 reactions intra?
Intra.
Yeah.
So we can have both, right?
Okay.
But for the most part, you're gonna see inter.
Okay. So that just means that there's not going to be reagents in an intra.
That's right.
Okay.
However, you might see a solvent. You're not gonna see the nucleophile like on the arrow, but you might see the solvent.
Okay. Thank you.
Okay. So we want to just kind of exhaust the SN2 reactions. So so in terms of, so when we look at the SN2 reaction, there are different aspects of the reaction that we have to consider. Alright, first of all, when we look at the substrate, what kind of substrate did we want?
Like methyl or an ethyl. I mean a methyl or a primary.
Okay, we can also have secondary. We just couldn't have the tertiary. And why couldn't we have the tertiary?
Because the tertiary would be too substituted and too crowded.
That's right. So we get steric hindrance. Alright, so for the substrate, we're gonna favor the methyl over the primary over the secondary. The reason because of this was steric hindrance. Right. So the reason why we're favoring the substrates in this order was because of the steric hindrance. Right? So one aspect of the SN2 reaction is the substrate. Another aspect of the SN2 reaction is the nucleophile. Okay? So what kind of nucleophile do we want?
I don't know.
One second, we kind of touched up on this before, kind of. Okay, actually we haven't touched up on this. So we haven't touched on this. I thought we did. Alright, so it turns out that we want a strong nucleophile.
And something is a strong nucleophile when it has more electrons.
We'll get into that.
Okay.
So in terms of nucleophiles, we want a strong nucleophile. I'll just give you a couple of examples of what would be a strong nucleophile. Right? So the first thing we're realizing here is that SN2 prefers substrates that don't have a lot of steric hindrance on there. Then SN2 prefers nucleophiles that are strong nucleophiles. And just to give you a couple of examples. So hydroxide would be one. Any OR group that's not sterically hindered. Anything like couple more. Alright, so we'll also add Br minus, iodine, cyano group. Right, and this one. These are all strong nucleophiles. Right?
Mm-hmm.
So let's look at what are some of the characteristics of these strong nucleophiles. So for one thing, they generally have a full negative charge.
What do you mean full negative charge?
Instead of it being partial.
Okay.
Right? So instead of having a partial negative charge, they have a full negative charge. So all the ones up there have a full negative charge.
Okay.
It's one thing. They don't have a lot of steric hindrance. They're not gonna have a lot of steric hindrance. They're gonna be like not all that large with small molecules, right? And the final thing we can say here is they can also be basic. You can say sometimes, or usually basic. Usually. So generally, there's a correlation between basicity and nucleophilicity. So strong nucleophiles generally are strong bases, but that's not always the case. So it's not always the case. Cool?
Mm-hmm.
So later down the line, you have to memorize most of these guys.
Okay.
But we haven't really gotten into how to determine what will happen and what. We're just going over each individual one. So then another thing that we can say is in terms of the solvent. All right. Now the solvent is going to be different from the nucleophile. The solvent is what we put the nucleophile in. Right? Right. So the nucleophile is bathed in a solvent.
Mm-hmm.
Right. The kind of solvent that we want for an SN2 reaction, we want a polar aprotic solvent. I'm sure you probably heard of this in class.
Mm-hmm.
Do you know what a polar aprotic solvent is?
I've heard of it, and I really do know what it is, but I don't remember right now, so.
It's okay. Alright, so the first keyword here is the polar. Right, so there it has some polarity, right?
Mm-hmm.
So an unequal distribution of charge.
Okay.
And then aprotic means that it cannot form hydrogen bonds.
Okay. Yeah.
So we're looking at solvents with unequal distribution of electrons.
Mm.
And we're also looking at solvents that can't form hydrogen bonds. Cool.
Mm.
So now let's look at some examples of these guys here. And so acetone would be one. If you see DMF, DMSO, and then we can have THF here. Right. So all these guys are examples of a polar aprotic solvent. So under the reaction arrow of an SN2 reaction, you might see an polar aprotic solvent. So like for example here, you know, maybe you might just see, you know, maybe in a case you might just see DMSO or something like that.
Mm.
Under the reaction arrow. Usually we do the SN2 reactions in a polar aprotic solvent. But that doesn't mean that it will not happen in a polar protic solvent.
Okay.
It's just more favorable to do it in a polar aprotic solvent.
Okay.
Alright. And last thing here we're going to consider here, we're going to consider the stereochemistry. Okay. Alright, so what kind of intermediate does the SN2 go through?
It doesn't go through an intermediate.
Okay. It turns out that the stereochemistry of the how does a nucleophile come in?
When the leaving group leaves.
Okay. Remember that it does a backside attack, right?
Okay, right at the 180 degrees.
That's right. So because we're going to be doing a backside attack, this backside attack that we're going to do is going to lead to an inversion of configuration. Alright. Now notice that inversion of configuration is not the same thing as inversion of stereochemistry. Inversion of configuration is not the same thing as inversion of stereochemistry. So inversion of configuration just means that the orientation of it would change. Right?
Inversion of configuration.
Yep. Now it turns out that so the inversion of configuration, it can lead to an inversion of stereochemistry, but it's not guaranteed.
Okay.
So it's possible that from the inversion of configuration we can end up with an inversion of stereochemistry, but it's not guaranteed. Right? And we'll take a look at an example. Oops, we didn't see this in your notes. Okay. So let's say we start off with alright. So let's say we start off with this guy here. Right? And let's say we react them with methoxide. Cool. So what's going to happen in an SN2 reaction? What would occur? So we're doing an SN2 reaction. What would occur?
You would just attack from the backside at 180, get rid of the halogen, your leaving group, and then it would come in as the nucleophile.
Okay. So this methoxide here is going to come in from the backside and then kick off this leaving group. Once this happens, we're going to get an inversion of configuration. Right? And this inversion of configuration can lead to an inversion of stereochemistry, but it's not guaranteed.
Okay.
Right? This is possible. So, all right. So what's gonna happen is that once this guy comes in from the back here, right? These three groups here are gonna be pushed this way, right? So this is gonna be OCH3, right? This carbon is this carbon here, right? And these three groups are gonna be pushed this way. So we will have this guy here, CH3. This guy here is going to be pushed this way, so he's going to be here, like that. You see that? Once this guy came in here, he pushed these two guys this way. That was the inversion of the configuration.
Okay.
All right. Now, the inversion of the stereochemistry is if we assign our priority values to these guys. So in this case, this is 1, right? This is 2. This is 3. This is 4, right? This fourth we focus on the fourth priority group, right? And since it's away from us, we keep the stereochemistry that we have. So in this case, is 1, 2, 3. We're going this way, so we have an S, right? Now, if we generate an S here, we did not get an inversion of stereochemistry. Alright? But if we generate an R here, right, then we would have generated an inversion of stereochemistry. Does that make sense? So the idea is that we will always get an inversion of configuration. Right? But that does not mean that you would always get an inversion of stereochemistry. Right? So in this case here, this is going to be 1, right? 2, this is 3, this is 4. Fourth priority group is away from us, we keep the configuration, right? In this case, this is S, right? So did we get an inversion of stereochemistry, or did we not get an inversion of stereochemistry?
No inversion. Right, because it's the same.
Actually, wait. Oh, I numbered these wrong. thought you would have caught this. You didn't catch it. Were you paying attention?
Yeah.
You sure?
Yeah.
Alright, so who has the higher priority? CH3 or the ethyl?
The ethyl.
Yeah, so I got these guys mixed up. The only reason why I knew that I was wrong was because, well, I'll point to it in a little bit. So we get an R. This is an R.
And that's an inversion.
That's right. The only reason why I knew that it was an inversion and I didn't get an inversion was because of the fact that this guy here is 1. So the nucleophile here has a priority of 1, right?
Always?
No, I'm just saying, and this is what we determined, right?
Okay, yeah.
And this leaving group has a priority of 1. This is what we can say, right? If the nucleophile that's coming in and the leaving group that's going to leave, if they both have the same prioritization, priority numbers, then we will definitely get an inversion of stereochemistry.
Okay.
But if they have different numbers, then we might not get that inversion of stereochemistry.
Okay. Can we write that?
So if the nucleophile and the leaving group have same priorities inversion of stereochemistry. Okay, so now what we want to do is we want to get into the SN1 reaction.
Yeah.